the introduction, Ambika. And my talk is going to be about what's next in AI, right? So, how many of you here are working with some form of an AI technology today? If you can just give me a quick raise of hands. So it's like maybe 10, 20%, yeah, of the audience. So I think AI technology has a long way to go, right? It's not easy to work with. Now let's ask some other questions. So what programming languages? How do you program your AI applications? For those of you who are, or forget AI, right? What languages do you program in? So let's see a show of hands for who's using Python. It's pretty much, I would say 80%, 90%. What about, how many people use Java? It seems to be on the down slope, maybe, I don't know. How about R? Some R users. And C++? Not much. How about JavaScript? So some JavaScript users. So, given that we are in an analytics and a data science conference, it's not surprising that people are using the more dynamic languages. So before I jump into my presentation, I'd like to introduce my colleagues. So we have Dhairya Gandhi. So just say hi, and we have Deepak Suresh. So they've helped me immensely prepare this presentation. And another reason you should meet with them after my talk is because they have some Julia stickers to hand out to you. At 1 o'clock, we also have a workshop. So if you would like to start, learning Julia, just keep that in your mind. There is a workshop here at 1 o'clock that they'll be conducting. Okay. Now with that, how many of you have heard of Julia before this talk? So I say, and how many of you are using it? That's disappointing. So definitely go to the workshop. This is so Julia is the language of the future, and this is why, right? In the past, if the experts wrote the algorithms typically, so and many of you might be sort of considered domain experts here, and you write them in Python or SAS MATLAB. These languages tend to be typically dynamic in nature, interactive, easy to use. And then typically for development, because the dynamic languages are slow, they're not high performance, you end up rewriting the programs in C++, C#, Java, whichever one you want to deploy your solution in. And it's inefficient, right? In order for companies to actually win in the market, the basic idea is you need to take your products and get them to market the fastest. So if you did not need to write your application twice, right? Once in Python or R or MATLAB, and then again in C++. What if you could have the ease of use of the dynamic languages and the performance of the deployed languages? This is the motivation with which we designed the Julia language. So, it gives you immense levels of performance while being simultaneously easy to use. Now, my presentation is roughly going to be in two parts. So I'm going to talk a little bit about Julia because not everyone might be familiar with it. And then I'm going to talk about what is happening in the world of AI and differentiable programming with Julia. But in order to set some context, I have some quotes here. The top one is from Yann LeCun, who's a recent Turing Award winner for his work on deep learning. And he put out this tweet that deep learning is dead. Long-live differentiable programming. And then we have this quote from Andrej Karpathy, who builds the AI stack at Tesla, who talks about the software 2.0 world, right? That in many kinds of applications, increasingly we won't be writing algorithms or code, but instead we will actually be working with models and data in order to sort of meet a business need. And then Chris Latner, of course, who's a famous compiler author and the author of the Swift language, who's now working on machine learning at Google, talked about how Julia is one of the potential new languages in this field of differentiable programming. Jeff Dean, the head of Google.ai, he talked about how Julia running on TPUs. How many of you have heard about TPUs? Okay, everyone knows about GPUs, right? Everyone knows about GPUs. So Google has designed new hardware called TPUs, and it tends to be as fast as GPUs, but it has some very amazing benefits for deep learning and machine learning in general. And that's a tweet by Jeff Dean talking about how the combination of the best in hardware and the best language will actually make ML expressible and easy and fast. Now, everyone here who's working with deep learning knows that deep learning consumes tremendous amounts of data, right? And it's slow and it's expensive. Why is deep learning expensive? Because of the training cost. The training cost is huge. Inference is also expensive when you run it at scale, but training, especially on some of the larger models that we are seeing now, like GPT-2 and BERT and all these things, are very expensive to train. But not every field has enough amounts of data. Can you do machine learning with small data, right? That would sort of be a game changer if that was possible. And in order to do machine learning with lesser data, what you need to do is bring some domain knowledge into the problem. Now, by the end of my talk, I'll have presented various use cases to you many of them are scientific in nature, but what I'm claiming is that if you're able to combine your domain knowledge with machine learning, you will be able to get the best of both worlds. You'll be able to work with data in a domain that was not data-oriented before, but at the same time, you don't need huge amounts of data that deep learning algorithms typically need in order to do your trainings. Okay, so with that, I am going to jump into sort of a very brief and quick overview of Julia. It's a high-level language. Syntax looks like Python or MATLAB if you're familiar with one of these. The performance tends to be as fast as C typically, but in some cases it may be a little slower because it's a dynamic language, but not more than 2x slower than C code. Python, on the other hand, can often be factor of 10, 20, 40 times slower than C. And here's a Mandelbrot function, so it's a simple function that's calculating the Mandelbrot set, and that's what Julia code looks like. So just looking at it, it looks like a standard, you have a function, that's what the for loop looks like. You have a conditional statement in there. You can see the math in there. Just pretty straightforward, very clean syntax. It's not white space sensitive like Python, so I think that's a positive in my mind. Performance-wise, compared to some languages like Python and R and Octave and MATLAB, Julia can be easily at least 10 times faster. So the way to read this performance chart is that it is showing the speed up over C. So a C program is right here, right? So if you're here, then you're as fast as C, and then this is a logarithmic chart, so 10 times slower, 100,000 and 10,000 times slower than C. As you can see, all the Julia benchmarks are bunched up around being as fast as C, whereas if you look at the Python column, they're kind of shooting up, and some of the examples are over 100 times slower than C. And I think this should be a convincing slide that if you need to write a high-level program in a high-performance language, Julia is the best way to go forward. Lots of customers, partners, companies using Julia. All the big companies that you know of are using Julia in some form or shape. In fact, Julia Computing, which is a company that we formed to commercialize the possibilities behind Julia, we have seen downloads from over 10,000 enterprises today. You might be wondering, who knows Julia? Where do you learn it? Many of the universities today are already teaching Julia around the world, including many in India as well. It's still not as prominent as some of the other languages that you're familiar with, but it is growing very rapidly. I started the Julia project in 2009, and the first public announcement was in 2012. Ever since then, Julia has grown to become a project which has over 1,000 contributors to the language, almost 1,000 contributors to the language, over 3,000 packages, 13 million downloads. Our Julia paper now has over 1,000 citations. So it's just been a really fast journey. And if you look at sort of the uptake of similar languages, Julia is actually being adopted at a much faster rate than Python or MATLAB were in their time. It was recently covered in Nature. Of course, Analytics India magazine has been writing about Julia for a very long time, so I would encourage you to stay on top of the news through their websites as well. Lots of books on Julia, so if you want to learn Julia, there are books that will teach you the Julia language, that will teach you computer vision, deep learning, data science, all these things. And often people come to me and ask me, hey, it's great we have this amazing new language, but if I don't have the libraries and the packages, I may not be able to actually get things done. And Julia has some of the best-in-class packages that are not even available in other languages. Packages for differential equations, for robotics, graph processing, operations research, biology, image processing, signal processing. So there are over 3,000 packages in Julia, but you can call any Python, R, C, or Java function from Julia without having to write or change a single line of code. So when sometimes people ask me how many packages are available in Julia, I say every possible package ever written, because you can pretty much call just about anything from Julia. Now, especially in the world of machine learning, Julia has a library called Flux. So think of Flux as something that is like TensorFlow or PyTorch, but is substantially simple and easier to use. Flux is actually just a few hundred lines of code. We often have students participating in the Google Summer of Code who are able to add a lot of code to Flux, who are able to fix it, do very interesting things with it. The MLJ project in Julia is actually something that is similar to scikit-learn. In fact, MLJ can incorporate scikit-learn under the hood, but it gives you a uniform API across all your different machine learning libraries. And then you have the Turing project, which is a universal probabilistic programming language in Julia, and it's one of the most cutting-edge probabilistic programming tools out there. I'm now going to talk about a few quick Julia use cases just to showcase how scalable and how widely used it is. So one of the largest problems that we ever ran in Julia was the Celeste project that ran on 650,000 cores, 1.3 million threads in parallel, right? So this is at a scale that actually required a supercomputer, and what it did was it took over 60 petabytes of astronomy data in order to identify all the visible light sources in the universe. So think of it as building a sky atlas, basically. And this thing was completely written in Julia by a very small team. On the industrial side, companies like Aviva use Julia for insurance modeling, and the Julia solution here was 1,000 times faster than the prior Java-based system. Clima is a modern climate and machine learning project, so where they're using machine learning to improve the efficacy of climate prediction models. And this is a new project with Caltech, JPL, MIT, and the Naval Postgraduate School in the United States. It is entirely using Julia and Julia's GPU stack and Julia's parallel computing capabilities to build the next generation climate science models. Personalized medicine in partnership with the School of Pharmacy at University of Maryland, Baltimore. In the future, starting very soon, when you go to a hospital, I hope none of you have to, but in case you do, the dosage for many of the drugs is increasingly going to start being calculated by a sophisticated product that is implemented in Julia. So instead of having an Excel-like calculator which doctors use, there will now be Bayesian models that are at the background that are accurately modeling the amount of dose you need in order to sort of avoid cases of undertreatment and overtreatment. Okay, so hopefully I've convinced you that Julia is here to stay. It's high performance. It can do things that none of the languages like Julia can do. But now let's dive a little bit further, right? So you might have been curious about, when I talked about machine learning with lesser data, how does that actually work, right? Now everyone knows that universal approximation theorem. If you're doing machine learning with neural networks, everyone knows that neural networks can basically, they are universal approximators, which means you can use a neural network to approximate any function. They are a universal approximator. So in theory, if your machine learning application is mapping an input to some kind of output through a function, a neural network can express that relationship. The question is, how do you find that function? And typically the way you find that function is through training, right? So you train your data, you start out with a random input function, and then you train your neural networks and create this universal approximator that works for you. The interesting thing is that neural networks are universal approximators which work very well in high dimensions. And this is not something that we still understand today fundamentally, but we have observed this anecdotally that when you're working with all these large image data sets and these large speech and text data sets, neural networks are somehow able to overcome the curse of dimensionality. And this is what makes them exciting and interesting for a lot of the machine learning problems. But everything is, learning everything from scratch is hard, requires tons of data and lots of compute. So how do we incorporate structure into our models, right? If I know something about the process that I'm modeling, then I should be able to give that information to my machine learning algorithm. And one would intuitively think that, rather than sort of having a system that is just training without any knowledge of the problem, if I can incorporate some domain information, I should be able to get there faster, right? And the way we do it is through the field of differentiable programming. Broadly speaking, if all of you remember your deep learning models, you have basically your neural network, you have your data, you have a loss function, and then you're optimizing the loss function, using an algorithm like gradient descent. And the key thing in the training of the neural network is the calculations of these gradients, right? That you have your data, you have your prediction, you have your loss function, and then you are sort of trying to improve the fit by, picking a gradient over the loss function and then improving your solution in the direction of the gradient. Now the gradient is where, today we are able to take most of the familiar deep learning toolboxes, whether it's TensorFlow or PyTorch, are able to only take gradients of very specialized structures like neural networks and so on and so forth, but not an arbitrary program. If you're able to take, if you're able to take an arbitrary function f written in Julia and then compute the f prime, which is the derivative of it, you can now have your loss function incorporate not just neural networks, but any arbitrary business logic, science, mathematics, anything you want, so long as you can differentiate it, you can optimize it, and because you're now encoding the structure, in the problem, not just as a neural network, but as your domain function, you're able to constrain the search space in a way that is only looking for solutions in the right part of the search space. So for example, convolutional neural networks encode spatial structure, right? So convolutions, they work with your neighboring pixels, and then the whole field of deep learning in computer vision has delivered and built these structures that are able to sort of figure out information from images. I'm not going to sort of try to explain why they work, but I would be sort of surprised to know if I would believe that almost everyone in the audience is using deep learning on images of some form or shape, and it's basically making use of these hierarchical and neighboring relationships in the pixels. But now, if we look at something that looks like a scientific experiment, right? So this is a model. I believe this is a model from systems biology, which is talking about reactions, right? So you have all these different reactions and their rates and how the system is evolving in time. If you want to combine this system with machine learning, you really need to encode this, this information into your project, into your program. So whether it's Newtonian physics or gene regulatory networks or any other complex phenomena, we can actually incorporate this into our scientific models. And I'm going to talk a little bit about it using our system. But here's something that I wanted to quickly show you. So here's the training data for this particular problem, right? This is all the data that's available, but the actual data looks like that, right? And by incorporating the structure of the problem into this training data set, we are able to, using Julia, accurately predict these complex set of dynamics in the time series that would otherwise be very difficult to do, right? By looking at just, so see, you can see that sort of the periodic thing, right, out there in the data. Now, the training data does not even have that, but we do know that it follows, you don't need to sort of think through the math here, but we have some equations that define, that we believe are describing this data. So we know some of the science here, but then some of it we don't, right? And what's happening in this training set is we're using some information that we know about the model, some information that we don't. We have a little bit of training data, but by combining them, we are able to sort of detect the complete time series with all these patterns that were not in the original data set. And it turns out to actually work quite well. So taking this to the next level, we are able to sort of apply this to something like a very large climate code. And not diving into the details here, The key thing is that by combining the machine learning with Julia's climate models, we were able to speed up the simulation by a factor of 15,000, right? So it's not a small amount of speed up that is possible when you incorporate your domain information into the models, into machine learning. You can get orders of magnitude of improvement by doing that. We've applied it to all sorts of interesting things like fluid simulations and so on and so forth. Now the tool that does this in Julia is called Zygote. It's a compiler pass that basically looks like this. So you might remember the Julia code that we looked at on an earlier slide. Here's the power function. It's just calculating x to the power n. And so for example, 5 to the power 3 is 5 cubed, it's 125. And if you needed to compute the gradient of this function, all you say is gradient and give it the function as the input and the value at which you're evaluating it, and you get the answer. So the answer here is 75. If you work through the math of what is the derivative of x to the n, it should be nx to the n minus 1. And anyone want to compute that? So I have 5 cubed, right? So the derivative will be 3 times 5 square. 5 square is 25. 25 times 3 is 75. And that's what Julia calculated for you. But the way it did that was by applying automatic differentiation to this program, right? It did not do the derivatives that you and I were taught in school, where where you're doing it symbolically, right? It actually did it on this program, on top of that for loop and everything else, on the while loop, right? This is actually quite an impressive accomplishment by the team that has built this. And it's literally just that. You take any program F, and you can get an F prime. Now, don't get me wrong. It does not just work on any possible program you throw at it. This is a field of active research and development. But it can handle quite, given a few constraints, it can handle quite a large different number of codes. Sorry? Yes, it can do partial derivatives as well. Yeah. So in fact, Zygote is the tool that is used underneath Flux for all of all of the ResNet trainings and everything that you do in Julia. Sorry, I don't know who was speaking, so I'm not sure I can see you, but I hope I've answered that. So this is an example of applying Zygote to the colors package in Julia, where we are now using gradients over colors in order to sort of pick the right kinds of colors and an optimal color difference scheme. I'm going to say a lot of things that probably are without context, and I'm hoping that you'll go back and Google them if you're interested. But each of these topics itself is a complete talk, and I'm not able to do it justice. This is what a typical deep learning model in Julia looks like. This is your, just your WX plus B, the kind of thing that you might use in MNIST. So you can see what the chain looks like. You have the WX plus B up there. You have your inputs, and then you get your loss function, and then calculate the gradient, and then you can do the gradient descent. Here's your gradient calculation right here, and then this is your gradient descent step. So this is all there is to it in Julia. When you're working with Python, you're looking at codes that are in Python or C++ under the hood, and you cannot even look at what's going on under the hood. But in Julia, you're actually able to sort of just work with this on the fly. Can you tell me how much more time I have? Oh, right there. Okay, thank you. All right, so I'm going to skip through a lot of these things so that I can actually, show some code at play. This is an example of a trebuchet. Let's see. I'm going to actually skip the training of this trebuchet, but what's happening in here is you have a trebuchet that is, if you watch Game of Thrones, right? You have a trebuchet that's trying to aim, and we have applied differentiable programming in order to solve the inverse problem, that given this stone and the distance that I have to throw it, given the current wind speed, what angle should it be aimed at? And we trained a neural network on a trebuchet simulator so that it can now solve the inverse problem. In a simulator, you know that given the input weight, what distance it will go, right? That's what Newtonian physics will tell you. But if I have to throw it at a target, then I need to solve the inverse problem, that I know the distance, what angle should I release it at? And traditionally, you could have done this with mathematics, and you could have calculated the derivatives by hand. It turns out that the trebuchet dynamics are quite complex, and you don't actually have to learn them. You can just take the simulator, throw it into the Zygote tool, calculate the gradients, and move on. And then even just a few minutes of training on my laptop, and it will sort of be able to hit the target. And we even incorporated wind speed in here, so that it can even sort of get the accuracy right for wind speeds that it has never seen before. This is your typical cart pole example, typical reinforcement learning takes 400 episodes to solve the cart pole in order to balance it. With differentiable programming, we just get it down to 6 because we're able to differentiate the equations that lead to the balancing. So it's not truly reinforcement learning, but you have the code, you have the simulator's equations under the hood. You can differentiate the simulator, you can solve it orders of magnitude faster. Similar applications in pharma, in computer vision, in computational finance, in quantum computing. This is the inverted pendulum, how to balance it. Sort of one more level of complexity than the cart pole. So I'm going to skip all this stuff, and I'm going to actually switch to some demos. But before I do that, this is what Julia Computing does. This is what we all do. Dhairya and Deepak Suresh work with me, and we build Julia, the programming language, all the differentiable programming tools, and provide products in order to deploy these things at scale. So if your company is interested, please reach out to us. But in the meanwhile, let me show you what some of this looks like now. Oh my God. Okay. I think I've run this just before, so maybe I'll be fine. This is so one of the things that when you work with data, you always have to load the data fast, right? So no point doing machine learning if your data loading step is slow. And this notebook here just shows you how Julia's CSV reading compares with Pandas. Now everyone imagines that Pandas is a very high quality library, which it is, by the way, and it's amazing. And we're sort of loading this kind of a data set here, right? So it has a few columns of data, and this is what the first 5 rows look like. This is what Python 3 and Pandas does. It takes 676 milliseconds in order to load it. Julia does it in 229 milliseconds without multi-threading. But now one of the key things is that Python or MATLAB, all these languages are not multi-threaded. So you can only use one core unless you've written a C function that is multi-threaded under the hood, which everyone knows is extremely painful to do. Julia, on the other hand, is multi-threaded. So any Julia user can literally just put an annotation in front of their for loop and multi-thread their program and use all the cores on your laptop or your server. And once we turn on multi-threading for Julia's CSV reading capabilities right here, all you do is say threaded equals true, you get a speed up. So how many processors was this run on? 8. So on 8 threads, you're getting a pretty substantial speed up here, right? You're getting like almost like a factor of like 5, I would say. I don't know who's speaking, and I can't hear you, sorry. I'd request you to wait until the question answers and maybe use a mic. Yeah, because I really can't hear you very well. So give me 5 more minutes. And here's the second run. So this file was about 150 megabytes. Here's a 1 gigabyte file. Python's taking 6 seconds, and we have Julia doing it in 3.5 milliseconds with threading. So without 3x faster with single threaded and 15x faster with multi-threading. So just CSV reading, right? And the entire program for CSV reading and parsing in Julia is written in Julia itself. There's no fancy tricks under the hood, which R and Pandas have to do in order to make it work. Now here's another simple example, and this will really demonstrate the power of composition. Everything in Julia composes, right? If you write a program and you write a program in Julia, the design of the language is such that they can compose very well, even though you may not have collaborated for those 2 programs to work together. They often end up working together. So Julia's data frames library, Julia's machine learning libraries, Julia's automatic differentiation libraries, they were sort of not designed originally to work with each other, but they just do. This is not what you see, right? You don't typically see libraries in other ecosystems that were written without the knowledge of others collaborating or composing that easily. Here's an example. XGBoost. Everyone here knows XGBoost decision trees. And we have a simple data set here. This is the mushroom data set, it turns out. And the data set looks like right here. It's 6,000 things with it's a matrix of 6,000 by 126. Okay. Here we define the parameters. It's just standard XGBoost stuff, nothing fancy. We define the loss function, except that in this case, the loss function has been slightly modified so that it penalizes false positives and false negatives differently. And this is what the loss function looks like. Now this, you could sit down and work out the derivation of how to calculate the gradients and the Hessians. So this is what the derivation looks like. Some of you might be able to do it. Some of you might not. Some of you might find it to be too complex. Some of you might just do it in your sleep. But I think the right way to do it is to not do it at all, right? You just let Julia do it, As if you watch the movie Matrix, right? It says, why send a man to do a machine's job, right? So we give this simple logic, we take these functions and just give it to the gradient function, and out comes your gradients and Hessians, and you can just pass them back right back to XGBoost. So this is amazing, right? You have XGBoost, a library that does not know about Julia, that's doing its usual thing, but now we are able to plug in Julia's compiler and automatic differentiation capabilities, and then run this entire optimization and problem and get done. So, and now you can just go back and modify. You can play around with this, right? If you wanted to use a slightly different function, you can just edit it right there and throw it back and get it. You don't have to rederive this thing over and over again. And my last quick one, I know I'm out of time. Oh, I have 5 more minutes, okay. So here's an example of the UNet. This is a complex deep learning model. It kind of looks like this. Whatever this is. If you want to know more, you could talk to Daria right here. But it's complex, whatever it is. And this is what the model looks like. We've got a sample images from the data set. This particular image is used to detect pneumonia. So this kind of an image has pneumonia. These ones don't. I'm not a doctor, and maybe many of you are not. So, but this is what it is. Define all the layers. This is the okay. So here's your UNet model, right? This is how all the layers are being combined together. And the key thing I wanted to show here is this model was defined completely in Julia, right? That's all the code you need, nothing more. You can write the entire UNet thing in Julia from scratch and run it on your CPU. But of course, now everyone wants to run on GPUs because that's much faster for all these matrix operations or array operations that you see in deep learning. And Julia actually compiles to GPUs natively, okay? So if you go to the Julia GPU website, you'll be able to see this, juliagpu.org. But you can literally take a typical Julia program, not a completely arbitrary Julia program because GPUs are not as general as CPUs, but programs that can be effectively run on GPUs, you can write them in Julia, run them on CPUs, and just send them to the GPU with a simple function like this, and send the data. That's your model GPU of u, GPU of x and y is your function, and you can literally just run it. So here's the model running on the CPU. It took 43 seconds, and here's on the GPU the same model. It took 140 milliseconds. So 300 times faster. You did not have to write CUDA and GPU kernels and all that other stuff. It pretty much just works out of the box. Now, if you're using PyTorch, maybe they've written the GPU kernels for you for all the common use cases you need. But the moment you need to do something different, like in the earlier XGBoost case, right? What if you needed your own loss function? What if you needed to change something? What if you're not solving a standard model? You are pretty much unable to do it using a framework. The only way to do it is using a language by being fully general, by having a compiler under the hood, and by having tools that can be layered and stacked on top of each other so that you get the benefit of the complete system and the entire optimization of the whole program. So with that, I'm going to stop my presentation. And do I have time for some questions? OK. Oh, just please use a mic, whoever it is. Yeah.
Hello?
Yeah.
Can you hear me?
Yes.
Yeah, you mentioned that the Julia is written in Julia. Does that mean the compiler is also in Julia?
That's a good question. So a lot of the things that you use here in the Julia packages are written 100% in Julia. a large part of Julia is also written in Julia, except for the parts that like the Julia parser and some of the garbage collection routines, which are written in C. But I would say about 70 to 80% is in Julia itself.
No, but how does that work? I mean, recursively, you would have to keep. I mean,
It's you know, I mean, C compilers are written in C, right? So it's not it's being done for the last 40 or 50 years.
no, I'm not
Yeah.
a CS person, so I mean, I'm just fascinated by this whole.
Yeah,
fact that- yeah.
it's probably not a question I can address right away in the 2 minutes, but you might want to Google self-hosting compilers, and you know that's how they do it. It's tricky, right? So being completely Julia written in Julia is very tricky, but having most of it done is not difficult.
Hi,
Yeah.
my name is Indrajit, and I just have a question regarding the meta learning. PyTorch Meta is the library that used for meta learning.
Okay.
Do you have any such libraries in Julia for meta learning?
Do we have libraries in Julia for you know, we have our machine learning experts here more than me. Yeah. So the answer is yes.
So, and where can I find it? I mean, if you have to do it, like in.
I would suggest find them after the talk or
Sure.
go to the 1 o'clock session.
Yeah. Thank
Yeah.
you.
My question is on using Julia for embedded systems.
Uh-huh.
Would you recommend that? And if you do so, are there any known projects that are?
So Julia runs very well on ARM. You can download Julia distribution for ARM just by going to julialang.org. It just runs on the Raspberry Pi. So if you have a Raspberry Pi level embedded system, Julia and a lot of its packages just work. It also works on Jets and Nano. What it will not work on is an Arduino. Okay? Yes. Oh, I can hear you, yeah. The question was, what is a good application of differentiable programming today, and you know, maybe compare it with conventional programming. So conventional programming is simply computing. You know, if I write a program to compute f of x comma y comma you know, z, right? That's a conventional program. Differentiable program is computing f prime of x comma y comma z by applying your chain rule, but at the program level. You know, when you learn chain rule and differentiation rules in school, you don't learn what to do with the for loop, right? You don't learn what to do if an if statement comes. And there are all sorts of complexities that arise when you do these things, but the Julia compiler is able to do that on Julia programs. Differentiable programming is actually an idea that has been around for a very long time, but it has been brought to the forefront with deep learning. Deep learning is a special case of differentiable programming, where we found a particular structure of programs that could be efficiently differentiated, put on GPUs, and run at scale. The question is, can you do it with more broader programmatic structures? And that's the generalization of what we do in deep learning today is called differentiable programming. That is not just for one class of models. We want to generalize it across, you know, any program. Now, generally, if you can compute an f prime, you can optimize, right? Because if I have a derivative, I know in which direction I have to go in order to reduce the loss. And if I can do an f prime of typical of more arbitrary functions, I can solve different kinds of problems. So an example, so a lot of scientific examples, for example, logistics operations, right? So think about a linear programming or quadratic programming. All these you know, libraries typically need a gradient, often even a Hessian, in order to get you know, to do the optimization. So then they have nothing to do with deep learning. You're just solving a large, you know, railway routing problem, or a cell phone tower planning, or bandwidth, or anything you have, right? Wherever you're doing optimization requires you to reduce the loss, and whatever the complexities in your F, if you can deal with more complex functions, when you differentiate, you can do more things. I hope that helps. Yeah.
Thank you so much. In the interest of time, can I request for further questions, you can meet Viral offline. I'm sure he'll be happy to help you. Thank you. Can we thank him with a round of applause? Thank you, Viral.
Thank you.